Good morning, good afternoon, good evening, wherever you may be in this part of the world. Welcome to another session of my presentation, and this time is routine testing of power transformers. We'll go through all the routine testing parameters that you need to know as a discipline engineer, maintenance engineer, operator, or maintenance technician, or project engineer as needed when you have to perform this type of testing on the power transformer. My good name is John Kweku Otu, and I'm a professional electrical engineer for the past 31 years, and I'm based in the United States of America. Now, let's talk about this. Once you watch my video and you like it, don't forget to select the like button, and also don't forget to share, and don't forget to select the subscribe button. And below is the name of my YouTube channel that has tons of learning presentations for your career, to develop your career and grow your career. And for you young engineers that are upcoming, it's an opportunity for you to start learning and developing yourself. Okay, so now let's talk about the different routine tests that can be performed on a power transformer. And this routine test can be done for a new transformer that is being manufactured on the factory floor, or a maintenance level for an in-service transformer that is in operation. Right. Okay, so now the first thing we need to talk about is the oil breakdown test, right, or dielectric breakdown test. Okay, so for this one, what you do is right before the transformer is going to be taken out of service, right, or offline, then that is when you collect oil samples, right? So when you collect the oil samples, right, you have to basically take a note of the top oil temperature. You also want to take a note of the winding temperature, which is basically the hotspot temperature, right? You also want to take note of the ambient temperature, the humidity level, right? So these are all the information that you need as you collect the oil sample before you take the transformer offline. On the other hand, too, you can also, right immediately after you de-energize the transformer, then that would be the time that you can collect that oil sample. Either way, that works, but it shouldn't be longer. It shouldn't be longer than when you take the transformer offline. So basically, you collect that oil sample and send it to the lab, right? Same you need for this measurement of moisture, right? Okay, so you take it to the lab. What you can do is you can have most of the utilities have a setup where they have their own lab, right? And to basically perform this basic testing, right? But for comprehensive testing, then that is when you need an external lab, right? So you can do that and basically, take oil samples and basically take it to your internal lab. Then also take it to an external lab where a comprehensive testing can be done. Okay, so what is the purpose of the breakdown of oil, right? Okay, so for a mineral oil, right? As you know, transformer, has mineral oil, and also can have natural ester oil, right? And natural ester oil is basically, based on they call it a vegetable oil. Right? Okay, so let's take an example for mineral oil, right? During operation of a transformer that has a mineral oil, due to contamination, right? Due to thermal stress, due to electrical stress, right? Due to oxidation, acidation, right? All based on moisture intrusion, oxygen, etc. Right? Basically degrades the oil, right? And basically lowers the breakdown voltage. Basically, the dielectric breakdown voltage is based on the philosophy of the oil to withstand higher voltage, the required voltage, say, due to lightning surges. That will be the maximum, right? Basically, that defines the basic insulation level. Okay. So that is when basically the testing is done to make sure that the transformer has back capability and the oil is not degraded. So the criteria is basically it has to be greater than 52 kV. That should be the minimum. right? And the criteria also can be graded and classified based on the voltage level of the transformer, right? So for transformers where the high voltage side is below 69 kV, they have a different criteria of acceptable dielectric breakdown voltage. And also between 69 kV and 280 kV, they also have an acceptable criteria. And greater than 280 kV on the high voltage side, they have an acceptable um, criteria of a dielectric voltage. So the value that I gave to you as 52 kV or 60 kV, it's for power transformers that have a high voltage side greater than 280 kV. Similarly for moisture, right? The goal is to minimize the moisture level in ppm, right? Parts per million, right? Okay, so that itself also is being classified. The criteria level is being classified based on the voltage level. Okay, so below 69 kV, they have a certain criteria that is supposed to meet. Then between 69 kV and 280 kV, it has a certain criteria that is supposed to meet. Then greater than 280 kV on the high voltage side, it has a certain criteria of moisture that it's supposed to meet. I think below 69 kV, I think it's 28 ppm, and in this one is about 24 ppm, and greater than 280 kV is about 20 ppm. Okay. Next, routine test is a voltage ratio, right? So the voltage ratio, it's basically ratio measurement to basically determine the ratio based on the high voltage and the low voltage winding voltage, right? So basically you impress the voltage on the low voltage side and measure the corresponding voltage on the high voltage side and to determine the ratio, right? And you compare the results with the factory test nameplates, right? Okay, or the factory test results or the design results, right? Then you determine the difference, and the difference shouldn't be more than plus or minus 0.5%. During the testing of the voltage ratio, the polarity is also determined, and the vector group was also determined, right? Okay, so the vector group, basically, if you have a D, Y, and one transformer, right? Okay, so the delta, the high side is basically wound in the delta, and the low side is wound in the Y, N, right? Okay, so this one is basically the phase shift, right? So basically what we are doing is to verify this phase shift between the high voltage side and the low voltage side. So that is what the test is about. And in addition, the polarity, right? The polarity is basically to determine the instantaneous level of current and direction of current flowing into the polarity and out of the polarity, right? So the high voltage side is into the polarity and the low voltage side is out of the polarity. So that is when we do this testing. Next is winding resistance, right? Okay, so basically we do the testing for the winding resistance for the high voltage side winding and the low voltage side winding, right? Okay, so for the high voltage side winding, we determine the winding resistance and basically correct that resistance to a temperature of 80 degrees or 90 degrees Celsius. Similarly, for low voltage winding side, the same thing. We determine the resistance of the winding and basically could do a correction to a temperature of 80 degrees or 90 degrees, right? And what is the purpose of this testing? Is to determine broken strands, broken connections, right? Tap changer problems, de-energized tap changer problems, right? So that is the purpose of this winding resistance. And basically, if you have a transformer that has many taps, right, the winding resistance is done for all the tap positions, and basically the results are compared with basically the factory acceptance test values, or let's say for an in-service transformer, that transformer has been in operation for, let's say, 20, 30 years. Then basically you compare it with the last results and make sure that there's no significant delta or gap in between the current results and the old results. Next is a measurement of copper loss and impedance test and load loss tests, right? Okay, so basically for a factory test and routine test, right, what you are doing is basically doing this test. Basically during this test, like I indicated, the low voltage side is short circuited, right? And voltage is applied, rated voltage, a percentage voltage is applied to the high voltage side. Let's say 10% of the high voltage side is applied. So if you have a 230 kV rated transformer for the high voltage, 10% of it is 23 kV. So 23 kV is applied until you reach a rated voltage. Rated voltage is achieved on the secondary side, and based on that, you measure the copper loss, and basically from that, the impedance can be determined, and the load loss is determined. The low loss is equivalent to your copper loss, right? So the low loss becomes an input during the temperature rise test, because the low loss is added to the no load loss to give you the total loss, and that total loss is what is fed into the transformer based on the wattage. Right? The current, the wattage is equal to the current and the voltage, right, times √3. So that is the amount of wattage that is fed into the transformer during the temperature rise to determine that your transformer temperature rise meets design criteria. Next is polarity, right? And polarity, I think we did discuss it over here. Next is excitation current, right? Okay, so this is the no load loss test, right? Okay, so for this one, they call it open circuit test, right? Okay, so where basically, you know, you have the transformer over here. You have a measuring ammeter, right? You have a voltmeter. Then you have a wattmeter, right? Okay, in phase, and the wattmeter is in phase A, phase B, right? Okay, so the low voltage side is open circuited, right? It's open circuited, right? And basically, all the measurements that you perform is to determine the amount of no load current that flows to the magnetization branch of the transformer, and that is considered the core loss or the no load loss. And you add the no load loss or your core loss to your load loss or your copper loss, and basically to determine the total loss of the transformer. All right. So the excitation current basically is performed to determine defects, damage, failure of the core of the transformer. Right, the laminations, right? If there are laminations, insulation degradation, which basically results in defects, right? Basically, the excitation current is going to show you. It also manifests, broken strands, 10 to 10 shorts, right? If you have that condition, it's going to show in your excitation current. And in evaluating the excitation current, you look for pattern, right? Okay, so you have phase A, phase B, phase C, right? The pattern of phase A, phase C current, excitation current should be the same. And phase B should be higher than both, right? So you do that, usually the testing is done for each tap level, right? So that is when, so anytime that you see not a routine or just an abrupt change in excitation current, then basically that calls for concern for further testing to be confirmed that. Next is insulation resistance testing, right? Okay, so insulation resistance testing is done utilizing DC voltage, and basically the testing is done at 1,000 volts at DC, 2,500 volts DC, 5,000 volts at DC, or 10,000 volts at DC, right? That is basically injected into the high voltage winding or the low voltage winding, and basically the insulation resistance test is done. So the testing is done for high voltage to ground, low voltage to ground, and in between the high voltage winding and the low voltage winding, right? And the purpose is to determine contamination level, right, in the paper insulation and the oil insulation, right? So furthermore, beyond that, you can also perform them. You can determine the polarization index testing. The insulation resistance testing is done starting from 0, 30 seconds, 1 minute, 2 minutes, 3 minutes, all the way incremental of 1 minute, all the way up to the 10th minute, right? So the value you get for the 10th minute insulation resistance, you divide it by the value you get for the 1 minute resistance to determine the polarization index testing value, right? Okay, so the criteria for polarization index is for a new transformer, it should be greater than 2, right? So it means your insulation resistance testing at 10 minutes over your insulation resistance at 1 minute should be greater than 2.0. But for an in-service transformer, or a transformer that has been in operation for greater than 5, 10 years, 10, 20 years, 40 years, then basically 1.5 and above is acceptable. Below 1.5, then basically that calls for concern, and further investigation, right? Okay, so next is induced voltage, right? Induced voltage basically it's a test basically to determine basically the major insulation, right? High voltage to ground components of the major insulation, right? Low voltage to ground, and in between the high voltage um, to the low voltage, and also turn to turn insulation, right? That is when we perform the induced voltage. Right? So for the performance of the induced voltage, let's say if you have a 230 kV transformer, right, and or let's say 13.8 kV transformer and 480 volts, right? So for the low voltage side, the testing is done for each side, each terminal, right? So for the low voltage side, if it is rated at 480 volts, right, about 2.3 times this value will give you the amount of voltage that you need to apply, right? So you apply it to the low voltage side with the high voltage side floating. And likewise, if you have a 13.8 kV high voltage side, it's about 2.3 times that value. That is the amount of voltage that is applied with the low voltage floating. And the purpose is to basically determine all the major and minor insulations components. Make sure that there is no degradation in that. Then furthermore, for a new transformer, that is when PD monitoring is also done. Then power factor testing, right? Okay, so that is the tan delta, right? Okay, so basically that determines the contamination level in the oil and the paper insulation, right? Okay, so acceptable value is 0.5% and above, right? Okay, so for a new transformer, it should be I take it back. For a new transformer, the acceptance level is 0.5% and below. Okay, for a new transformer, it shouldn't be more than 0.5%. It should be less than 0.5%. But for a service age transformer, a transformer that has been in operation for more than 10 years, right? Okay, you should expect something between 0.5% and 1%, and nothing more than 1%. If you obtain power factor testing of more than 1%, then basically that calls for concern for further testing to be done to confirm what the problem is, right? So that is when basically you combine this testing with the DGA testing and also oil breakdown testing and moisture testing. So those are all the other testing that you do, and compare the results and analyze the results to find out what really is going on. If you should have a power factor testing results that is greater than 1%. Next is applied potential. That is high pop, right? They call it separate source, right? Okay, so basically what you're doing is basically to determine the performance of the major insulation as well too. So that testing is done for the high voltage side and also for the low voltage side, right? Then you can also go to the further of testing the CTs that are in the bushings and below the flange level or the turret of the transformer, where the ratio of the CT is performed and the polarity of the CT is also, and magnetization saturation curve is also performed. You can also go to the extent of performing the insulation resistance of the CT at a voltage of 250 volts or 100 volts. Right. With that comes to the end of my presentation, and thank you for your listening. Liaison. Look out for my next other presentations, and don't forget to visit my YouTube channel, and don't forget to, if you like this presentation, select the like button and subscribe. Select the subscribe button. Right. Thank you.